Welcome everyone to this week Autonomy Talks. This week is a pleasure to have Dr. Nan Li, who is recently graduated from University of Michigan, working with Professor Ilya Kolmanovsky and Anouk Girard. So something about Nan Li, currently is a postdoctoral research fellow at University of Michigan. Before that, he received a Bachelor of Engineering in Automotive Engineering from Tongji University, and subsequently obtained a Master of Science in Mathematics and a Master of Science in Mechanical Engineering from the University of Michigan. His research interests are in stochastic control, game theory, multi-agent systems, safety-critical systems, and their applications to human-centered autonomy, and in particular autonomous driving. And today he will talk about some of the recent work he has on these topics, and we are all very, very interested in what he's going to tell us. So without further ado, Nan Li, the stage is yours. Go ahead.
Thank you very much. Thank you for inviting me and introducing my background. It's my great pleasure to have this opportunity to talk about my research. So the title of this talk is Game-theoretic Methods for Safe Autonomous Vehicles on Shared Roads. I will skip this slide about my information. So this diagram shows the major components of an autonomous vehicle. And my research has been focused on the planning and control of autonomous vehicles. And in this talk, we will focus on the behavior planning or decision-making and vehicle-level control. Firstly, as background, autonomous vehicle technology promises to bring safer, cleaner, and more efficient transportation, as well as improved mobility and independence for seniors and people with disabilities. It is projected that in the near to medium term, autonomous vehicles will operate on roads shared with other users, including human-driven vehicles. In this case, the complexity and uncertainty due to extensive interactions among road users necessitate advanced decision and control systems that can properly account for these interactions to ensure safe and effective autonomous vehicle operation. Meanwhile, the development and high-confidence validation of such systems have been recognized by the automotive industry as among the biggest technological challenges and must be addressed urgently. In this talk, we will discuss game-theoretic methods for autonomous vehicle control. Firstly, game theory is the study of strategic interaction among rational decision makers, and we will apply game theory to study and model driver interactions in traffic scenarios involving multiple vehicles. Indeed, game-theoretic methods for autonomous vehicle control have been investigated by several researchers in these publications, including some publications from our group. Game-theoretic methods have several advantages, especially compared to pure data-driven or learning-based methods, including, firstly, game-theoretic methods can typically lead to solutions that are interpretable, because these methods are based on mathematical formulation of the problem with certain psychophysical interpretation. And secondly, game-theoretic methods can typically lead to solutions that are effective for a range of scenarios. In contrast, pure data-driven or learning-based methods typically lead to solutions that are effective for the specific scenario of the data set. And lastly, game-theoretic methods are typically data light, which means these methods usually require less amount of data compared to pure data-driven methods. This is important because it has been reported that multi-vehicle interaction scenarios in released traffic data sets are insufficient, and this fact largely limits the practical application of data-driven methods, but in this case, game-theoretic methods can be applied. All right, after the brief introduction of the background and overview, let's move to the technical part. The first technical part is game-theoretic modeling of driver-to-driver interactions. So we will apply game theory to study the modeling problem of modeling driver interactions. For this, we will model a traffic scenario as a dynamic game defined by these 5 major components. Firstly, we have a set of drivers or vehicles. This Si represents the state of vehicle I, and this board S represents the aggregation of the collection of the states of all vehicles, and is referred to as the state of the traffic. This AI represents the action of driver I, and this board A represents the collection of all drivers' actions. We will use a transition map capital T to describe traffic dynamics, and this map T maps the current traffic state to the next traffic state as a result of all drivers' actions. And each driver has a reward function representing his or her driving objectives. And the important feature here is that a driver's reward depends not only on her own state, but also on other vehicle states. For instance, to reflecting collision status, and also on other vehicles' actions. And this fact reflects the interaction nature of such a problem. Then we will consider driver models. A driver model is defined by these 2 major components. Firstly, we have an observation model, which describes how a driver perceives the traffic environment. And we have a driving policy, which describes how a driver reacts to her observations. And in general, this transition map capital T, this observation model O, and this driving policy pi can be stochastic maps. All right, let's take an intersection scenario as an example to better understand how to define the components of the dynamic game. Firstly, for an intersection scenario, it is reasonable to assume the vehicles will drive along pre-planned paths, which can be expressed as a function capital P. With this pre-planned path P, vehicle's motion can be described by the kinematics along the path. This rho here represents the distance traveled along the path. This v represents the speed along the path. And this a is the acceleration input. This theta represents the vehicle's heading angle. And we can collect all the variables here to define the vehicle state as. And a driver action is a value for the acceleration input, A. And the driver's driving objective can be represented using a reward function. And we can consider a reward function as a linear combination of several terms to reflect different considerations, such as collision avoidance, maintaining a reasonable separation from other vehicles, and maintaining a reasonable velocity. So these variables and equations here can be used to define the components in the dynamic game to represent a traffic scenario. All right, then let's discuss some specific game-theoretic models. In this talk, I will introduce 2 modeling methods. The first one is called LevelK reason-based models, and the second is called leader-follower-based models, or Stackelberg-like models. I will introduce these 2 one by one. First, the LevelK reasoning-based models. LevelK reasoning is a behavior model describing human behavior in interaction scenarios. In LevelK reasoning theory, human behavior is classified according to levels of reasoning. In particular, a LevelK agent behaves as if she best responds to the belief that all the other agents are level k-1. So in short, a LevelK agent optimally responds to level k-1 other agents. So this is the K assumption in LevelK reasoning theory. LevelK reasoning theory has demonstrated improved accuracy in predicting human behavior over conventional analytic methods, including, for instance, Nash equilibrium-based methods in a range of behavioral experiments. Let's take this simple intersection scenario involving two interacting vehicles as an example. At first, vehicle B may choose to maintain its current speed and go through the intersection first. So this thought represents a reasonable driving behavior, but without really accounting for the interactions between these two vehicles. And this thought can be classified as a level 0 behavior. Then A may think B will go first, and in this case, I should yield to B. And this represents a best response to the level 0 behavior of B and can be classified as a level 1 behavior. And B may continue to reason and think A will yield to me, and in this case, I can go ahead of A safely. And this thought represents a best response to the level 1 behavior of A and can be classified as a level 2 behavior. So effectively, level 0 represents reckless driving behavior, i.e., reasonable driving behavior, but without really accounting for vehicle interactions. Then, as the best response to such reckless driving behavior, level 1 represents cautious or conservative driving behavior. And then, as the best response to level 1 behavior, level 2 represents relatively aggressive driving behavior. Mathematically, we can define LevelK driver models according to this formula here. Specifically, LevelK driver model or LevelK driving policy of vehicle I is the optimal policy, maximizing the expectation of a cumulative reward over a certain planning horizon, such that the ego vehicle, vehicle I, takes actions according to this policy, and most importantly, all other drivers take actions according to some level K-1 policy. So how to use this formula to construct level K driving policies? Firstly, we can design a level 0 driving policy, which represents reasonable driving behavior, but without accounting for interactions. Then we can plug the level 0 policy into this formula here. Then use this formula to compute and construct a level 1 policy. And once we have the level 1 policy, we can plug it back into this formula here and use this formula again to construct a level 2 policy. So this way, we can construct level K policies for K equal to 1, 2, 3, up to arbitrary level, following a sequential and iterative process. And in practice, we choose to use reinforcement learning to train level K driving policies. This diagram here illustrates the procedure of using reinforcement learning to obtain level K policies. Firstly, we will construct a traffic environment, which are determined by vehicle's equations of motion, observations, actions, drivers' revolve function, and certain road parameters. Then we will design a level 0 policy and let all the vehicles in this traffic environment be controlled by this level 0 policy. And in this case, this environment can be called a level 0 traffic environment. Then we can put a learning agent, which is a new vehicle, into this traffic environment and use a reinforcement learning algorithm to train this learning agent and obtain an optimal policy for this level 0 traffic environment. And by definition, this policy will be a level 1 policy. And once we have level 1, we can feed it back into this traffic environment, i.e., we let all the vehicles in this environment be now controlled by this level 1 policy, put another learning agent in this environment, use reinforcement learning to train it, and obtain a level 2 policy. So following this loop and this iterative procedure, we can construct or obtain level K driving policies for K equal to 1, 2, 3, up to arbitrary level in a iterative and sequential procedure. This plot here shows the training results of level 1 and level 2 driving policies. Let's now look at some simulation results of LevelK drivers for highway scenarios. This animation on this left shows a simulation with a mixture of LevelK drivers, which are obtained using the reinforcement learning procedure introduced in the previous slide. And these two videos shows the implementation of our LevelK driver models in the high fidelity driving simulator Talks. Talks is a high fidelity driving simulator. So this way we can implement our driver models in such high fidelity driving simulators to obtain improved traffic simulation. And this slide shows some simulation results of the LevelK models for intersection scenarios. These two animations shows the interaction between three vehicles controlled by different combinations of LevelK models. So these two simulations start from the same initial condition, but because these cars are controlled by different combinations of LevelK models, which represents different combinations of driving styles of these drivers, we can see the simulations evolve differently. We have also validated our LevelK models using traffic data. Here, the plots on top shows the trajectories of vehicles in the real-world traffic data set. And the plots at the bottom shows the simulated trajectories of the vehicles using our LevelK models. And we can see the actual trajectories and the simulated trajectories closely match each other. And this means our LevelK models can accurately reproduce real-world traffic scenarios. All right, then let's move to the second modeling method, which is leader-follower based models. The motivation for this method is that in many traffic scenarios, a driver's behavior is dominated by her intention, whether or not to yield the right of way to others. For instance, at an intersection, which car goes first depends on their driver's intentions to proceed ahead or to yield the right of way. And similarly, for highway merging scenarios, which car goes first usually depends on their driver's intentions to yield. And motivated by such an observation, we exploit the leader-follower asymmetry in Stackelberg game theory to represent drivers' intentions. And in general, a leader represents a driver who intends to proceed, i.e. not yield, and a follower represents a driver who intends to yield. Mathematically, the leader and follower policies can be defined using the following set of equations. Firstly, a follower policy is an optimal policy that maximizes the cumulative reward under the worst case due to the uncertain action choice of the other vehicle. By the way, this set of equations here defines the models for two vehicle interactions. And a follower policy is basically a max-min strategy to represent the intention of yielding the right of way. And then a leader's policy is an optimal policy maximizing the cumulative reward under the assumption that the other vehicle is a follower. So this set of equations defines the leader and follower models for the case of two vehicle interactions. Then we can extend the models to n vehicle interactions using this set of equations. Here, this I smaller than j represents that I is the pairwise leader in the vehicle pair ij, and I greater than j means I is the pairwise follower in this pair. And this model here accounts for all interacting vehicles based on pairwise leader-follower interaction. And using this model, we can successfully model and simulate the interaction among multiple vehicles. And here there are some pictures showing several real-world intersections in Ann Arbor, and we can reproduce these intersections in the simulation environment and use our leader-follower based models to simulate vehicle interactions at these intersections. All right, so we have introduced the LevelK reason-based approach and the leader-follower based approach for modeling driver interactions. Let's now compare these two methods. Firstly, LevelK models focuses on the representation of the heterogeneity of driver behavior due to different driving styles. Recall that level 0 represents reckless driving behavior, and level 1 as the best response to such reckless driving represents cautious and conservative driving behavior. And as the best response to level 1, level 2 represents aggressive driving behavior. And in this case, the LevelK models may be most suitable to be used for scenarios where a driver's behavior is largely influenced by her driving style, such as on highways. In contrast, the leader-follower based models focuses on the representation of the heterogeneity of driver behavior due to different interaction intentions. Recall that a leader represents a driver who would like to proceed, not yield, and a follower represents a driver who would like to yield. And in this case, the leader-follower models may be most suitable to be used for scenarios where a driver's behavior is dominated by her interaction intentions, such as at intersections or force merge scenarios. Combination of both methods may lead to further improved models, and this is being currently investigated. Now let's discuss some applications of these game-theoretic models. The first application is to use these models to construct interactive traffic simulator. So this video shows the implementation of our LevelK driver models in the high-fidelity driving simulator talks, which is then used as a platform to run simulation-based testing of autonomous vehicle control algorithms. Another application is to use such interactive traffic simulators as environments for training autonomous vehicle control policies via reinforcement learning. So if one wants to train some autonomous vehicle control policy using reinforcement learning, he or she needs a training environment, and our game-theoretic driver models can be used to construct such training environment. And lastly, such models can also be directly used in trajectory prediction modules of autonomous vehicle control systems. And I will discuss this application in more detail in the second part of this talk, which is interaction-aware autonomous vehicle control. Recall the background. Autonomous vehicles will operate alongside human-trained vehicles, and one of the biggest challenges yet to be solved is decision-making and control for autonomous vehicles to operate safely and effectively in the presence of extensive and uncertain vehicle-to-vehicle interactions. This motivates the development of an interaction-aware autonomous vehicle control framework, which is based on integration of the previously developed game-theoretic driver interaction models with Bayesian inference and model predictive control. This framework has several advantages or features. Firstly, this framework leads to control solutions that are interpretable, because in this framework, we use game-theoretic driver models for trajectory prediction. Secondly, In this framework, we online quantify interaction uncertainties and reduce such uncertainties based on observed trajectories and Bayesian inference. And lastly, and maybe most importantly, this control framework leads to solutions with an explicit probabilistic safety guarantee under such interaction uncertainties. This control framework can be illustrated by this diagram on the right, and it has three major components. Firstly, we have a model inference block, and then a trajectory prediction block, and lastly, a trajectory planning block. And I will introduce these three blocks one by one. Firstly, we consider an MPC-based control strategy for the autonomous vehicle. The autonomous vehicle optimizes a sequence of actions to maximize the expected value of the cumulative reward over a certain horizon. So this cost function represents driving objectives. And this optimization is subject to traffic dynamics, which can be described by the transition model capital T introduced previously. And this ST represents a measurement of the current state. And lastly, we use this probability condition here to represent safety requirements. Specifically, we require that the probability that the predicted states to be within some safe set over the planning horizon, we require this probability to be greater than some specified threshold. For instance, this safe set can represent the requirement to keep the distances between vehicles be greater than some safe radius. By the way, the equations here corresponds to the case of two vehicle interactions, i.e. the autonomous vehicle interacts with one other vehicle. But these equations can be easily extended to handle multiple vehicle interactions. Note that in this optimization problem, we have this variable A2, which represents the actions of the interacting vehicle, which are not control variables and must be predicted. And we can use a game-theoretic driver model for the prediction of their values. So we can modify this MPC problem into this form. Note that now the expectation in the cost function and this probability in the constraint are now conditioned on the assumption that the interacting vehicle or the interacting driver takes actions according to some game-theoretic driver model pi. And with this pi, these A2 variables can be treated as state-dependent disturbances. So this optimization problem is well defined and can be solved. However, due to the a priori uncertain driving style and the intention of the interacting driver, which is referred to as interaction uncertainty, it becomes necessary to consider a set of driver models instead of a single one. For instance, we can consider LevelK driver models with different K values to represent reckless, conservative, or aggressive driving style. And we can consider the leader and follower models to represent behaviors under different interaction intentions. Then the question becomes which model to use or how to synergize the predictions of these models in an optimal way. So this involves the model inference block. And in this block, we use a recursive Bayesian estimator to combine our observed state trajectory and our previously applied action trajectory, as well as the predicted state trajectories from these models to compute a posteriori belief distribution over the model space. And this belief distribution is basically a probability distribution over the models conditioned on all available data. Roughly speaking, this posteriori belief B sub t represents a quantification of interaction uncertainty. And as we gather more and more data, we can improve our belief in these models, which means uncertainty is reduced. And now we can modify the MPC problem into this form. Note that now the expectation here and the probability here are conditioned on the current belief B sub t. And we can expand these expressions here into this form. So this conditional expectation here can be expanded as a weighted sum of the expectations conditioned on the assumption that the interacting vehicle takes actions according to some model pi of I, and the weight for this expectation is our belief in this model pi of I. And we can expand this conditional probability using in a similar way. So this basically means we are assigning weights to the predictions of different models according to the posteriori belief in each model. And this way, we can automatically account for the interactions of all the models based on our vast knowledge of the driving intention and driving style of the interacting driver. All right, so this set of equations defines the trajectory planning block of our control framework and completes the entire control procedure. Now, let's look at whether this control framework works. So for this, we consider a case study which represents a highway on-ramp merging scenario. Highway on-ramp merging is a quite challenging scenario, even for human drivers, because such scenarios typically involve extensive interaction between multiple vehicles. To implement our control approach, we consider the three nearest vehicles as interacting vehicles and treat and assume all other vehicles drive at constant speeds. We consider a revolve function as a linear combination of 5 terms, which represents a penalty for collision, a penalty for going off-road, some reward for maintaining reasonable separation from other vehicles, some reward for approaching the target lane, and some reward for maintaining a reasonable velocity. We also consider some constraints on the speed and maximum acceleration. And in our MPC problem, we consider a planning horizon, which corresponds to 4 seconds of local head time. And we update our decision at a frequency of 4 Hz, which means we resolve the MPC problem and update our control decision at every 0.25 seconds. And in this example, we use the leader and follower models to represent the interaction behaviors of these interacting vehicles. And this means we consider a model set consisting of 2 models, which are leader and follower models. This slide shows some simulation results. This top animation shows a case where the vehicles 2 and 3 are leaders, and the vehicle 4 is a follower. And in this case, the ego vehicle controlled by our interaction-aware control approach decides to merge between vehicles 3 and 4. And in this animation, in this simulation at the bottom, the vehicle 2 is the leader and 3 and 4 are followers. And in this case, our controller decides to merge into the gap between vehicles 2 and 3. So these 2 simulations start from the same initial condition, but due to different driving intentions of these 3 interacting vehicles, the simulations evolve differently. But in both cases, our controller can successfully select a proper gap to merge into, because our controller can successfully and correctly identify the intentions of these three interacting vehicles. So our control approach seems to work pretty well in these simulations, and we are interested in knowing whether this approach can have reasonable behavior in real-world situations. So for this, we choose to use the US11 traffic data for such validation purpose. This data set includes a route section like this, which consists of one on-ramp merging area, and we will focus on the merging behavior at this on-ramp area. So we identified in total close to 200 merges at this area, and our controller succeed in merging in 193 cases and failed in 5 cases, which corresponds to a success rate of 97.5%. So this success rate is pretty good because this data set represents quite busy traffic involving many vehicles. So this is a challenging scenario even for human drivers. And our controller can succeed in most merging cases. So in particular, our validation method is to replace the merging vehicle in the data set with a vehicle controlled by our controller and let all other vehicles drive following their original trajectories in the data set. Then let's look at some specific success cases. So in this first case, the driver in the original data set decides to merge behind this vehicle 2, which is probably a big truck. And our controller also decides to merge behind this vehicle 2. And the reason for this behavior is our controller identifies this vehicle 2 as a leader, which means vehicle 2 will probably not yield to us. So in this case, we decide to merge behind it. And if we compare these two animations, we can see the actual trajectory of the real human driver and the simulated trajectory of our controller closely match each other. Let's wait for a second. Right, we can see the trajectories of these two blue cars match each other pretty well. Then let's look at a second case. In this case, the human driver in the data set decides to merge in front of this vehicle 2. And in this simulation, our controller also decides to merge in front of vehicle 2. And the reason is our controller identifies vehicle 2 as a follower, which means vehicle 2 will probably yield to us. And in this case, we can safely merge in front of it. Then let's look at this case 3, which is kind of interesting. In the original data set, the driver merges into the gap between vehicles 3 and 4, but at a quite early stage. Let's look at this again. Right, this original driver merges quite early, and our controller decides merge relatively late, but also into the gap between vehicles 3 and 4. Right, so here our vehicle slows down and merges into the gap between 3 and 4. And I will explain the difference. I will explain the reason for causing this difference after we look at the next case. Then let's look at some failure cases, which might be more interesting. So in this first failure case, the original driver merges into the gap between 2 and 3, but we can see, firstly, this driver also merges quite early, and the distances between these three vehicles are quite small, which represents relatively dangerous merging behavior. And in this case, our controller fails to merging into the top limb. And one important reason is that in our simulation, we penalize length changes during this red shaded section. So that's why our controller does not choose to merge within this section. Let's look at this again. And after we pass this red shaded section, we can no longer find an acceptable gap to complete a safe merge. So this also means our controller can avoid unsafe or dangerous merging behavior. Then let's look at the second failure case. In this case, the driver in the original data set drives between two lanes for quite a while, and this forces this vehicle 2 to slow down and let it cut in. But in our simulation, our controller fails to do such a thing. And one important reason is that in our validation approach, all the other vehicles drive following their original trajectory in the data set. And this means these vehicles are not responsive to the behavior of our controller. So that's the reason why our controller cannot do such a thing to force vehicle 2 to slow down to let us cut in. This represents both a limitation of our current design of the controller, but also a limitation of our validation approach. So for next, we would like to improve both. All right, so we have introduced the interaction-aware autonomous vehicle control framework. Let's now try to draw some summaries. Firstly, in this talk, we showed that game-theoretic methods can be used to generate interpretable models to represent heterogeneous interaction behavior of road users, in particular vehicles on shared roads. And these models can be used to create interactive traffic simulator for virtual testing and reinforcement learning-based training of autonomous vehicle control policies. They can also be used in trajectory prediction modules of autonomous vehicle control systems. And we have developed an interaction-aware control framework for autonomous vehicles on shared roads by integrating the game-theoretic models with Bayesian inference and MPC. And in this framework, interaction uncertainties are explicitly accounted for. And this framework leads to control solutions with an explicit probabilistic safety guarantee. And the last remark is game-theoretic methods can be quite useful, and they can also be applied to other multi-agent and human-robot interaction problems beyond autonomous driving. And this completes my presentation. Thank you very much for your attention, and I'm happy to take any questions. Thank you.
Thank you, Nan, for the talk. Thank you very much. So are there any questions from the audience?
Hi, Nan. Thank you very much for your talk. I had two questions. So one was regarding the first part of the talk, when you were showing the Bayesian update about the others' trajectories. I was wondering, how do you parameterize the models on which you do the update?
Let me see.
I think it was some there maybe. I think you just posted.
The first part or the second part?
I think it was in the second part when you were showing the Bayesian update when you were doing the prediction of the trajectories.
I see. This?
There was another diagram, maybe, yes, here. So how do you parameterize? Yeah, I think I was referring to the next slide, but it's the same.
I see. These models are represented using a neural network. So it's basically a stochastic map from the state to the distribution of actions, and we have use a neural network to represent a model, and the inputs to the neural network is current traffic state, and the output is a distribution of actions.
But how do you discretize the space of the models? So when you have the belief over the models of the others.
So we in this framework, we do not, or in this approach to parameterize the models, we do not need to discretize the space, but we need to discretize the action space.
Okay, and then you put the belief on the actions.
Yes.
Thank you. Now, the second one was really related to the last part of your talk, where you were showing this testing of the controller on say on passive data, which you said at the end, it's to some extent limiting because you're testing an interactive controller on data that are fixed or static.
Yes.
So what do you think? What do you think could be a good, say, testing framework for these kind of things?
So our current thought is to let the nearest vehicles that may have relatively extensive interactions with us to be controlled by some other driver models. For instance, some car following models. So in our current validation approach, generating these results, we let all the vehicles follow their original trajectories, and this means they in this vehicle's mind they are not actually interacting with us. But for next, we would like to first we initialize the scenario according to the positions of and velocities of these vehicles in the data set, and then we let the nearest vehicles be controlled by some driver models, for instance, car following models, so that they can react to our actions.
Okay, thank you.
Yeah, thank you.
Any other question?
I have a question.
Go ahead.
Sure, please go ahead.
In regards to the LevelK reasoning,
Mm-hmm.
if you can go back to that one.
Yeah.
So what is the difference between that and terminating best response early, like an iterated best response?
The idea is similar, but the solution, the specific solution will be different.
This slide is good. So that's the procedure of how you get it.
Sorry, I missed your second sentence. Can you repeat it?
So this equation is the procedure of how you calculate the K-level policy.
Yes.
And
so
that
the
looks
LevelK policy.
Like an best response iterations. So can you comment on the difference?
So there is a maybe the biggest difference is, so if we look at this formula here, the actions of the interacting agents are feedback. So they take actions according to some feedback policies, which means their actual actions will respond to our choice of actions. But based on my understanding, if you do iterative what's it called? Iterative.
Iterative best response on the policy level, not on the action level. So it would also be best response on the others' policies.
I see. In that case, these two methods may be similar, but I need to investigate more details. So my previous understanding is the iterative best response is on the action level.
And does this only work if the players have different K levels, or does it work if all of them have the same K level as well?
So in our simulations, we observe that if all the vehicles are, for instance, level 1, which means all the vehicles are relatively conservative, then they can still resolve their conflicts pretty well. But if all the vehicles are reckless or all the vehicles are aggressive, then they may lead to some collisions.
Okay, so
So basically, in this approach, a LevelK policy, a LevelK vehicle only optimally responds to LevelK -1. If all the agents are LevelK agents, then the policy does not lead to any performance guarantee.
Thank you.
Yeah.
Right, then there is a question from Jason Heath that asks, have you proved stability guarantees for the combination of the different models?
Is this question related to the control framework at the second part?
I can ask Jason to either unmute or specify via the chat. Oh, it says yes.
Okay. So here, although we refer to this approach as a control approach, but actually it deals with a high-level control, or actually the decision-making level. So in this case, we do not investigate stability of this controller in details. So the action here basically represents a reference trajectory, and we will use lower level controllers for instance, trajectory tracking. And in that case, we need to handle stabilities. Does this answer your question?
Yes, it says thank you.
Okay, thank you.
Great. Any final question, final comment? Doesn't seem so. So none. Thank you very much for your talk.
Yeah, thank you very much.
And good luck for your next steps, for your just started postdoc.
Mm-hmm.
And yeah, thank you very much again.
Yeah, thank you very much. Yeah.
Thank you.
Have a good one, everyone.
Bye-bye. See you all next week.
Yeah, bye-bye.
Thank you. Bye-bye.